Today we are going to start a topic subject known as electronic devices. Now this subject essentially involves how a semiconductor device like say a diode, transistor, photodiodes, photodetectors, Zener diode, avalanche diode, these things, how they actually work in tandem. Now this subject is somehow different from analog circuits in the sense that analog circuits generally involve the application of the semiconductor device in a particular circuit like transistor biasing, FET biasing, MOSFET biasing and so on. But what happens in case of this electronic device, this subject, here we deal mainly with how the device behaves internally. What is the mobility of the charge carriers? What are the charge carriers? What should be the direction of current? Why should be the direction of current be in that particular direction? And this. Essentially, here we look at the internal details, or rather, here we go inside the device and try to find out how a device should behave. Okay. Generally, semiconductor industry or this electronic industry is based on something called a semiconductor. Now, what do I mean by a semiconductor? By the term semiconductor, what I mean is that it's a something intermediate between a conductor and an insulator. This is best shown by something called a band diagram, energy band diagram. An energy band diagram looks something like this. Energy band consists of three layers. One is the conduction band, one is the valence band, and in between something called a forbidden gap. Now how does this energy band comes up? Right. These things we are going to discuss in about 5 minutes or so. But let us just assume that any kind of electron orbiting a particular atom lies in the valence electron shell, and hence the electron lies any electron that eventually conducts current lies in the valence electron shell. Okay. And if this electron is sufficiently energized, then it can break open from its valence shell and become a free electron. And it can become a free electron. This free electron is responsible for conduction of electricity. Now, there are some energy requirements. All electrons lie in something called the valence shell, and the energy of the valence shell is known as the valence band energy. When the electron becomes free and it starts conducting electricity, then the electron has a particular quantity of energy. This quantity of energy is called the conduction band energy. In between, it may, in any kind of a material, there may or may not be something called a forbidden gap. Any energy which lies in the forbidden band is not allowed for an electron for conduction of electricity. So, if an electron has energy equal to some energy in the forbidden gap, then it cannot conduct electricity. It cannot conduct current. Okay. So what happens in case of conductors? There are a lot of free electrons, which essentially means this valence band and this conduction band are in a mutual overlap. In case of a conductor, if this be my valence band and if this be my conduction band, so there is a overlap. Okay, and since there is an overlap, there is nothing called a forbidden gap. Since there is no forbidden gap, we apply any kind of voltage or we supply any kind of energy, the electrons starts conducting. What happens in case of a insulator? In case of an insulator, there is a gap between the conduction band and the valence band. There is a gap between a conduction band and a valence band. But this gap, this forbidden gap, is so huge and so big that if an electron lying in a valence band even if it is energized, it cannot jump into the conduction band. And unless and until it can jump into the conduction band, crossing the forbidden gap, it cannot conduct. So in case of insulators, this forbidden gap is very large, and thereby insulators are not able to conduct. But what happens in case of a semiconductor? In case of a semiconductor, this forbidden gap is neither negligible or equal to 0, nor the value is very high. This value is like an optimum kind of a value. This value is an optimum kind of a value. What do I mean by optimum value? Any electron here can jump across to the conduction band when a voltage or energy of a particular threshold is given. If the value of the voltage or energy is less than that of the threshold, then the electrons in the valence band of a semiconductor cannot jump into the conduction band. So, for a semiconductor, a threshold energy is required to make it conducting. Now let us go into the type of materials which we have as semiconductors. Semiconductor materials are generally of group 4. Now, why group 4? Because a group 4 element, if this be the nucleus, and these be the 4 valence electrons, so a group 4 element has equal affinity for donation of electron as well as equal affinity for acceptance of electrons. Equal affinity for donation and acceptance of electron to maintain its octet state. So, what it essentially does, a fourth group element, it forms something called a covalent bond. Okay. So it forms covalent bonds. Now, what are the fourth group elements generally we have? The fourth group semiconductor elements, what we have are mainly silicon, whose atomic number is 14, 1s2, 2s2, 2p6, 3s2, 3p2. So atomic number of 4, silicon, 1s2, then this is the distribution of electrons. What happens in case of germanium? The atomic number of germanium is 32. That's 1s2, 2s2, 2p6, 3s2, 3p6, 2s2, 3s2, 3p6, 3d10, 4s2, 4p2. This is the distribution of silicon and germanium. Silicon and germanium are the elements, are generally elements used in the semiconductor industry. Other than silicon and germanium, or other than group 4 elements, what we need, other than group 4 elements, we can have semiconductor by combining group 1, group 3 element with one group 5 element, such that the average becomes 4. So what are the group 4, group 3 and group 5 elements which we can have? Those combinations. Group 3 plus group 5, what we can have? We can have gallium arsenide. We can have gallium, aluminium arsenide. We can have gallium, indium phosphate, and so on. And so on. We can also have group 2 and group 3 elements, group 6 elements combining to get a semiconductor materials. Like for example, for group 2 and group 6 combining to form semiconductor material, we have zinc oxide, ZnO. Now, normal group 4 semiconductors are mainly are mainly responsible for conduction of electricity. Mainly responsible for conduction of electricity. Group 5 and group 4 elements, group 3 and group 5 elements are mainly used along with electricity, generation of electricity, for its photo characters. And group 2 and group 6 combined are used for as transparent conducting oxide. These oxides are transparent and they form a transparent semiconductor. Okay. Now coming back to the basic atomic structure of silicon, what we have. The basic atomic structure of silicon or germanium has 4 electrons in its valence orbit. Hence, one silicon combines with another silicon to obtain octet and stability. Now, since it has 4 electrons, it necessarily doesn't mean it has to combine with only one silicon and share all its 4 electrons with the sharing silicon atom. What it can do is this: one silicon atom can share its electron with 4 different silicon atoms as well, and this process continues. So the arrangement is something like this. So a silicon crystal looks something like this. Each silicon is bonded to 4 different silicon atoms in the adjacent cells, in its adjacent places. So we see this silicon has 4 electrons of its own. 1, 2, 3, 4. It gets 4 electrons from the neighboring 4 atoms. 1, 2, 3, 4. And thereby it completes its octets. Okay. Now along with silicon forms a covalent bond here, right? If it happens by any chance that a particular electron breaks its bond, Or suppose it happens that one of the electrons breaks the bond or has insufficient number of electrons to pair with. Breaks the bond and has insufficient electrons to pair with, then we say a hole has been created. In this case, a hole is nothing but an entity to describe that no electrons are present, but there is a possibility of electron lying in that particular position. Now, since we have holes and electrons, so hole is nothing but deficiency of electron, right? Deficiency of electron, which means hole has a charge of plus 1.6 into 10 to the power of minus 19 coulombs. Hole also can move like an electron. A hole also has a particular mass of its own, and so on. An electron, always remember, an electron for a silicon or germanium or any kind of conductor must be in the conduction region if it has to support current. Now, in the silicon band diagram, in the energy diagram, the lowermost energy of the conduction band is taken to be the threshold of the conduction band, written by EC. And the highest level of energy of the valence band is taken to be EV. Therefore, the forbidden gap becomes EC minus EV. Forbidden gap is nothing but EC minus EV. If the forbidden gap increases, then we approach insulator behavior. If the forbidden gap is reduced, we get conductor behavior. Okay. Now, in an intrinsic means nothing. There is nothing to disturb such a kind of a silicon lattice structure. In an intrinsic silicon, we have in case of intrinsic silicon, the total number of holes is equal to the total number of electrons that is found in the particular semiconductor for electrical stability. And another reason is that since holes are created from electrons, so obviously total number of holes would be equal to the total number of electrons. Now, how do we define current? Current is defined as number of electrons or charged particles that is flowing across a particular cross-sectional area in 1 second. So we can introduce something called a current density. What is current density? current density is defined by J and is given as the total current that is flowing through a particular cross-sectional area. Okay. Now, according to Maxwell's equation, current density is given by sigma E, where sigma is your conductivity. Where sigma is your conductivity. I will come to these things later. Now, how can we define sigma? Sigma can be defined as N Q mu N plus P Q mu P. Where mu is the mobility and N, P are electron and hole concentrations. The Q means the charge of the electrons and the hole. In either case, it's the same. Holes are sometimes written as H or as a positive point. Now we see that if this electron hops from here to here, we will get the electron here, but we will have a hole here. Similarly, if the electron jumps from here to here, keeping this extra space, a hole is formed here and the electron reaches here. Similarly like this. So, the direction of flow of holes is in this direction. The direction of flow of electrons is in this direction. In this direction. Now by convention, the direction of flow of electron is opposite to that of the direction of the flow of current. Hence the direction of flow of current, this is the direction of flow of electrons. So direction of the flow of current will be opposite to direction of the flow of electron. Or this should be my IN. Or rather IN, yeah. Now what is my total current? Total current is the effective contribution between the electrons as well as holes. Right? Electrons as well as holes. Now, since the direction of flow of electrons and holes are mutually opposite, that makes the electron current and the hole current in a linear path. Hence, we can say that the total current I is equal to IN plus I. Or the total current I is a summation of the hole current as well as the electric current as well as the electron current. Okay. So we see, and this kind of semiconductor I was discussing here is called extrinsic semiconductor, which essentially means that nothing impurity or nothing has been done to the semiconductor to manipulate its conductivity, resistivity, and other intrinsic properties.